Welcome back to ECE 320A. We're still working through this idea or technique of inverse Laplace transforming, and in this particular video what we want to look at or examine is performing the inverse Laplace transform when we actually have an improper transform to begin with. And I hope that you remember that an inverse or an improper transform means that the numerator polynomial is larger, equal to or larger than the denominator polynomial. It can be equal to, and we still have to perform the long division. Here's our example. We have a denominator that's either factored form or not factored, but our poles now are at locations s equal -1 and s equal -2. Those are the values of s that cause the denominator to vanish, which makes the transform itself go unbounded, and that's why it's called a pole. We have an infinite response at those locations. Here's our first question is, and I've already given the answer away in terms of this being improper, but let's go ahead and do that. The degree of the numerator, just to make sure we're all on the same page as far as what we're meaning by the degree, or I might refer to that as the order of the polynomial. It's the highest power of s in that polynomial. In this case, the numerator has degree or order 4. The denominator, if we multiply it out or count the number of, in this case, we have linear factors, so we have 2 of those, or we have a s squared in the denominator. I think it's clear that 4 is bigger than 2, and because of that, we have an improper transform, and we have to, prior to doing a partial fraction expansion, we need to divide the denominator into the numerator to then end up with a remainder that has a order strictly less than 2 or less than the order of the denominator. I've already given you this answer, but you should be able to conclude from this comparison of orders of the numerator and denominator, immediately say that, oh, we have an improper transfer function. It's not strictly proper, so we have to do some preliminary steps in order to start inverse Laplace transforming. As a sidebar, if you are fortunate enough to have a TI calculator that does symbolic manipulation, you can actually use one of the functions, proper fraction, prop frac, on this particular example, where now you might have x raised to the 4th plus 3x squared plus 2 in the numerator. In the denominator, you have x squared plus 3x plus 2. You put that information into proper frac, hit the enter key, and out pops the long division performed for you. You have now a polynomial x squared minus 3x plus 10. If x now is replaced with s's, we have s squared minus 3s plus 10, and our numerator now, they've actually factored out a common 6, but it's now minus 24s minus 18 if we've replaced x's with s's. I just use x's in my calculator because it's easier to find the x key than to find the s key. But that said, you can check your work if you are doing this by hand and doing long division. You can also pull out your calculator and invoke the prop frac function and find, hopefully, a check on your work. In this particular example, what we're trying to do now is rewrite f of s as a polynomial. So now we're trying to find these unknown coefficients, f sub 2, f sub 1, and f sub 0 associated with the polynomial that we need to pull out of the original f of s because it has a fourth order numerator and a second order denominator. And by doing that, we now have a numerator, n sub 1, that will have an order that's strictly less than the order of the denominator. We want to now find, via long division, n sub 1 of s. And we set it up just like we did in elementary school, except now we're doing it on polynomials. This particular numerator may be a little bit confusing or tricky because we've not included all of the different powers of s that actually are in that fourth order polynomial. And when you're performing the long division, sometimes it's nice to actually give yourself a reminder or bookkeeping step and include those terms with zero coefficients so that you don't gloss over them or lose track of them. Now what we want to do is do the long division just to illustrate what we're trying to ask you to do. In this case, we need to say, what do we multiply by s squared to obtain s to the fourth? That's not too hard. We need an s squared. So now we take s squared times the denominator and have s to the fourth plus 3s squared plus 2s squared. We can now compare that with the original numerator, subtracting the blue from the top equation, and we now have minus 3s cubed plus s squared. We now say, okay, how many, or what do we need to introduce in order to make s squared become minus 3s cubed? That's now a minus 3s. We now scale the denominator by minus 3s. We have minus 3s cubed minus 9s squared minus 6s. Again, comparing those, and we're trying to check the remainder to see when do we get a remainder after this checking or comparison that is strictly below in order or degree the degree of the denominator. The minus 3s cubes cancel. We subtract minus 9s from s squared, and we end up with 10s squared plus 6s. Now we check that remainder, which is, and we can bring down now the final 2 if we need it, and we say, oh, we have a second order remainder, but we still have a second order denominator, or we started with a second order denominator. We need to do one more step in this long division to get a remainder that's an order less than the order of the denominator. And now we need to say, okay, scale the denominator by 10. We now have 10s squared plus 30s plus 20. Comparing those, we end up with minus 24s minus 18. And now our remainder, comparing order of the remainder with the order of the denominator, is okay. And we can now say we can stop with this long division process. We now have our polynomial, s squared minus 3s plus 10, and the remainder n sub 1 that we wanted. Or we can now write capital F of s as f sub 2, which in this case was 1. That's what the coefficient is right here in front of s squared. We have minus 3 for the s, and we have now a 10 for the constant, and upstairs we have minus 24s minus 18, and I believe that this result of s squared minus 3s plus 10 plus this strictly proper piece is consistent with what we had from our calculator. So that now we can say, oh, we have 1 weighting the inverse Laplace transform of s squared in order to find the time domain expression for f of t. We have -3 weighting the inverse Laplace transform of s. We have 10 weighting the inverse Laplace transform of 1. And then we have to inverse Laplace transform this strictly proper piece, which has a numerator of -24s minus 18. Now, before we move on, let's just see what actually happens or what we obtain if we start inverse Laplace transforming a constant. We should have that in our transform table already. What happens when we inverse Laplace transform an s, and what happens when we inverse Laplace transform an s squared. Let's see if we can convince ourselves of what those look like in the time domain by just recalling some transform pairs. Remember, the Laplace transform of the impulse is now that impulse just sifts out what the argument of the integrand would be when that impulse acts, or in this case when it's on, which is at t equals 0. We evaluate the argument e to the minus st at t equal to 0, which gives us e to the 0 or 1. And now we have then that the Laplace transform pair, or the Laplace transform of an impulse, is 1. If we go in the other direction, which says, oh, I want to now assume that I have a S-domain expression that's 1. I want to know what does that look like in the time domain. I can inverse Laplace transform the blue equation on both sides. Now I have the inverse Laplace transform of 1 equaling the inverse Laplace transform of the Laplace transform of the impulse. Those operations cancel. So effectively you have no operation on the impulse, and we now have derived that the inverse Laplace transform of 1, or a constant, is the impulse. Meaning anytime you have a constant in the S-domain expression, that now correlates to an impulse, a quick function at, in this case, t equals 0, since there's no delay in that constant when it occurs. That constant is now for all time in the S domain, or it's a constant of 1. There's no shift. Now let's look at what happens if we were to find the inverse Laplace transform of something else, and that something else hopefully will be associated with this derivative of the impulse. So let's look at the Laplace transform of the derivative of an impulse, which is just going to be utilizing the definition of the Laplace transform of a derivative, which says that's equal to s times the undifferentiated Laplace transform's Laplace, or the Laplace transform of the impulse, minus the impulse function of time evaluated at t equal to 0 minus. The impulse is only active at 0, not at the left-hand side of 0 or the right-hand side of 0. The left-hand side of 0 is 0 minus. The right-hand side would be 0 plus. We want to know what's the value of the impulse right at 0. Well, that's when it's infinite, but to the left slightly at 0 minus, it's 0. That piece goes away. We just found above that the Laplace transform, or recalculated or re-verified that the Laplace transform of the impulse is 1, so that now we know that the Laplace transform of a derivative of the impulse, that's an odd beast, but just go with the flow. We now have the Laplace transform of an impulse is equal to s times 1 minus nothing, or it's s, so that if we now say, oh, let's inverse Laplace transform both sides of that expression, we now have that the inverse Laplace transform of s, a polynomial s, has an inverse Laplace transform, or its time domain waveform is now the derivative of an impulse. So anytime we see the inverse Laplace transform of an S in the time domain, that's the derivative of an impulse. And what you could do to maybe think about this, if you thought about an impulse being something like this with an infinite amount, an area 1 underneath that. So here's delta of t, and here's t. And let's say that we now have an area of 1, but this is going off to infinity in terms of magnitude, but the area, if we integrated that, would be 1. Well, we could start approximating that with something that's has the area of 1 and a very, very large amplitude, maybe a triangle. Then, so this is sort of the approximation of an impulse. If you now differentiate that, you can start to see, oh, on the left-hand side, if we're looking at the derivative of an impulse, we now have this positive value that's very large. On the right-hand side of the origin, we have a negative value. It's the slope is very large, and so you sort of see this very quick transition between a very large quantity and a very small very, very small quantity. It's big in magnitude or absolute value, but it's in the negative direction. So you have this sharp switching at time 0 when we're dealing with a derivative of an impulse. That's maybe a way to get some kind of insight into what in the world is the derivative of an impulse. Let's take that one step further. It seems to be working, so let's now take the Laplace transform of the second derivative of an impulse. That's now S times the Laplace transform of the derivative of an impulse minus the derivative of an impulse evaluated at 0 minus. Again, even though we have this sharp transition or switching, it's only happening at t equals 0. So at 0 minus, nothing is happening. This, again, disappears, and we're now left with S times S, or S squared is the Laplace transform of a second derivative of an impulse. If we do the inverse Laplace transform of both sides, we find that the inverse Laplace transform of S squared in the time domain, S squared becomes the second derivative of the impulse. Now we have a way of going from the frequency domain expression, S1, S squared, into the time domain. We've just learned that this piece is going to be delta double prime of t. This piece is now a delta prime of t, and this piece is an impulse. We, with long division, have just found what those coefficients or weights are. Here we have a -3. Here we have a 10. And we now need to do the partial fraction expansion of what's left, which is a strictly proper transform of -24s minus 18. So we want to now find the partial fraction expansion of capital F sub 1 of s. So maybe I shouldn't have done that. That's not quite right. This would be, let's say, let me do this up a little bit better. Let's now say that this piece is capital F sub 1 of s. That's the strictly proper transform. This piece we could think of as the time domain version of capital F sub 1 of s. That's maybe a more accurate way of denoting what we want. So we've now split little f of t up into parts, with the first parts being derivatives or not of the impulse function, and the second part, which is the traditional inverse Laplace transform of a strictly proper transfer function. Here we now have minus 24s minus 18. You can use your favorite technique. If we do the heavy side cover-up method, we could multiply both sides by s plus 1, and we have minus 24s minus 18 over s plus 2, evaluating at the value of s that causes the denominator term of a to vanish, which is minus 1. We now have minus 24 times minus 1 minus 18 over minus 1 plus 2, or that's 1 downstairs, and we have 24 minus 18, which now gives us 6 for the value of a. B is done similarly. Now we multiply both sides through by s plus 2, and we're left with minus 24s minus 18 over s plus 1, evaluated at the value of s that causes the denominator factor underneath b to vanish, which is s equal to minus 2. We now have minus 24 times minus 2. There's 48. Minus 18, that's 30 upstairs. We have minus 2 plus 1, or minus 1 downstairs. Or we now have b is equal to minus 30. Again, we could, with the calculator, obtain the partial fraction expansion using the expand function on that strictly proper piece, not on the whole piece, just on the strictly proper piece. We used proper frac on the whole thing to do the long division for us, and now we can write down f of t. We had the second derivative of the impulse with a scaling of 1. We had the derivative of an impulse scaled by minus 3. We had 10 weighting the impulse. So now the area under that piece of little f of t, if we calculated it, would have a value of 10. It's only active right at the origin. Then we have the inverse Laplace transform of 6 over s plus 1, which is now 6e to the minus 1t. And then we have the inverse Laplace transform of minus 30 over s plus 2, which in the time domain becomes e to the minus 2t. And that all is accurate or valid for t greater than or equal to 0. And that then shows or tries to illustrate the steps involved of inverse Laplace transforming an improper transform.